Okay, I think we can get started. So Eric, please go ahead.
Sure thing. So thanks, Rio and the organizers for organizing another Astro seminar. And thank you everyone for coming. Today, our speaker is James Paynter, who is a postgraduate student at the University of Melbourne down the road. His dissertation supervisor is Rachel Webster. And he'll be telling us today about intermediate mass black holes and gravitational lensing. So please take it away, James.
Okay, thank you for the introduction, Eric, and thanks so much for having me today. Yes, as Eric said, for those of you that don't know me, my name is James Paynter, and for those of you that do know me, it's unfortunate that we couldn't get together today and have this conversation in person, but alas, that's the way that the cookie hath crumbled. So this is some work that I've been doing in collaboration with Rachel, my PhD supervisor, obviously, since 2018, and with Eric as well for the past couple of years now. So I was originally looking at gravitational lensing of gamma ray bursts, and perhaps you can tell from the title, we found one, and we found that actually it was gravitationally lensed by an intermediate mass black hole. So these are the things I'm going to talk to you about today. So I'll just give you a brief outline. So first I'll talk about GRBs and gravitational lensing, and then I will, sorry, just setting up a timer. Then I'll dive into some data, and then talk about some recent discoveries in the field. Before going on, talking about, well, where are these intermediate mass black holes? Where could they be hiding? Why aren't we seeing more of them? And place our particular result in the context of intermediate mass black hole formation and supermassive black hole formation as well. Okay, so first onto gamma ray bursts. So here's a beautiful NASA graphic. And what is a gamma ray burst? Well, it's all in the name. It's a burst, a short flash of low energy gamma rays, high energy X-rays that signifies the birth of a stellar mass black hole. So in the case of long gamma ray bursts, you have a massive star going supernova, and that remnant that's left is a black hole. And as all this ejecta from the supernova falls back onto the black hole, forms an accretion disk, and shoots these two very powerful ultra-relativistic jets along the poles. And as the material from these jets travels along, turns from optically thick to optically thin, the energy is released as photons. And similarly, in the second class of gamma ray bursts, the short kind, two neutron stars merge, and that merger product, some of the material, well, most of the material accretes back onto that black hole, again forms the accretion disk, shoots the jets, and results in a gamma ray burst. Now, because these jets are ultra-relativistic, what we find is that the photons emitted are Doppler beamed. So not only is the number of photons increased, but also the energy of each photon is increased as well. And we find that because of this Doppler beaming, if you're along the line of sight, you see a very bright gamma ray burst. And if you're off the line of sight, you don't see anything at all, because all those photons are preferentially emitted in the direction of the motion of the jet. Okay, so what does this look like at the data? Well, on the left, we have a pretty simple gamma ray burst light curve. So it's called, the shape is called a fast rise exponential decay. Pretty obvious reason, fast rise up, exponential decay back down. Each of the four colors here are different energy bands. So 20 to 50 kilo electron volts in the red, and so on up to the highest energy channel, 300 kilo electron volts plus in the blue. So this makes up the vast majority of gamma ray burst light curves that we find, but there are more complex cases like this. But what we see looking at each of these individual pulses is actually, it's made up of lots of little fast rise exponential decay shapes. So this shape is ubiquitous in gamma ray burst data. Okay, now onto gravitational lensing. So the light curves I showed you were from a particular experiment, BATSE, which flew during the 1990s. And the main purpose of its mission was to determine whether or not gamma ray bursts were cosmological. And indeed, we know now that they are, thanks to this experiment. So we know that some fraction of the time, they will be gravitationally lensed. Now, quasars, which are another cosmological population, experience gravitational lensing, so multiple images, at a rate of about 1 or 2 per 1,000 quasars. Right, so each of these 4 images here is the same quasar experiencing gravitational lensing. Now, working in the favor of gamma ray bursts is that the universe is transparent in the 100 kiloelectron volt photon range, whereas quasars suffer from dust obscuration and the like. And furthermore, gamma ray bursts are sensitive to a much larger range of lens masses, so greater than 100 solar masses, whereas for quasars or galaxy-galaxy lensing, you need a very large lens mass, something like a galaxy, in order to split the images enough such that you can resolve that lensing has taken place. Otherwise, they would just all be superposed on top of each other. Now, unfortunately, gamma ray detectors actually have appalling spatial resolution. So rather than seeing this as 4 well-separated images, and since we're probing very small masses compared to a galaxy, that image separation is quite small anyway, what we actually do is see in time the effect of that gravitational lensing. So in the simplest case, we have a point lens here and then some distant source. And then here's us sitting on Earth, or perhaps with our telescope in orbit. And so in this case, if the source were perfectly aligned along this dotted line here, we would see a beautiful Einstein ring. So this ring, perfectly symmetrical, surrounding the lens. But as soon as we push that source off the direct line there, it breaks the symmetry and that ring becomes 2 separate images. Okay, so we have 2 different paths. And what we find is that obviously 2 different paths, both things traveling at the speed of light because they are light. We find that the one that actually goes the shorter distance but traverses deeper into that gravitational potential well of the lens will experience time dilation and thus arrive second. So this is the first arriving image and then the second arriving image. So there's some time delay between these 2 images arriving. So we see what we expect to see in a gamma ray burst is one burst and then sometime later another burst, which looks exactly the same as the first one. And so what we find is that that mass of that lens is directly determined within a factor of the redshift by a bunch of constants which we know quite well, we've known since high school, the time delay which we can measure, and some function of the ratio of the fluxes. So one of the images is going to be brighter than the other, and that's due to the focusing due to the gravitational lensing. So with knowledge of these 2 parameters, time delay and magnification ratio, we can find the mass of the lens within a factor of the redshift. But as we'll see, that may be, the redshift won't necessarily be known. Okay, and so here's a video of putting all that together that I made a couple of years ago now, procrastinating my master's thesis. So you can see gamma ray burst goes off. These are the photons now traveling. They become split. So there's some unknown lens in the middle. They're focused, coming back towards Earth, hitting the sun, or going past the sun, sorry, hitting the Earth, past the Earth, and arriving at our satellite. And so what we expect then in the light curve is some pulse. So the simplest case is just a fast rise exponential decay. Then some time delay later, in this case about 4 seconds, that same pulse repeated. And the simplest way, or a simple way, to look for this in the data is by autocorrelating this vector of this time series. So what that means is take the data, take a copy of it, and at each time bin, run it along for every time bin and correlate how self-similar the data is. And obviously when you're overlapping right at the start, extremely self-similar, so maximum correlation. Then if we shift it along, so now this pulse is Over here, well, no correlation because we're correlating something with nothing. But then if we shift this along so that it matches up here, what we find is that, boom, we have this peak again. So we come up with a way to identify the peak, and that will indicate to us, hey, this is a light curve worth checking out. Definitely good when you're searching very large data sets to have some sort of automation in place. And so from the equivalence principle, what we expect in our gravitational lensing is that all wavelengths of light are affected equally, which means we expect that the ratio of the fluxes in each channel going to be the same. So if this green peak is half the height of this one, then we expect this yellow peak to be half the height of this one, and so on and so on. And we expect the same time delays as well. Okay, and so we do this, and we found one very beautiful candidate with, you can see structure here is repeated here. This autocorrelation function looks almost exactly as we expected in the simulation I showed on the slide prior. And we find that if we do that for each of the 4 channels, that we get a similar peak in the autocorrelation function, and pretty much all at 0.4 seconds. Okay, so we interpret this as a gravitational lensing event. Okay, so it's now time for a statistical interlude. So I gave this talk, what was 2 years ago now, at the ASA in Brisbane, and I hope Eric will forgive me, but it was a good talk. Eric came up to me afterwards, a lot of questions, and he said, look, James, what you've done is fantastic, but it's not statistically rigorous. And thus he made me an offer that I couldn't refuse, hence this picture, which is that we would use Bilby and construct something more rigorous to determine that this candidate was in fact gravitational lens. Okay, so to do that, we need a model, and this is a model here describing the fast rise exponential decay shape that I mentioned previously. So we have this amplitude factor here, then some exponential, an asymmetry parameter psi. So that takes you from a symmetrical pulse shape and pulls you to one side, so makes you more peaked, and then sloped, coming back down. The duration scale tau, so that's just saying, well, I'm stretching this way, how long is the pulse? Is it 0.1 second or is it 10 seconds? And then this delta is telling me, hey, what time is that pulse starting? Okay, and so if we have a light curve with 2 pulses in it, and they're not related to each other. Well, obviously they came from the same burst, but not a gravitational lens. You expect that they would have different parameters. Whereas if it was a gravitational lens, you would expect that these 2 pulses are sharing those same duration and asymmetry parameters. The scale parameter is going to be different because there's the magnification effects, which will make the 2 pulses have different amplitudes. And there's a time delay. So obviously they will not share this horizontal shift parameter. But we have a single pulse, and then at some point later on, copy pasted by a demagnification, so a scaling of the amplitude, and then shifting it back with the time delay. Okay, and so we're going to compare a 2-pulse model and a 1-pulse lens model with each other. All right, so this is just fitting that single equation to one light curve. And so I made this little animation using Bilby, and you can see that it's iterating and then nicely arrives on what it thinks is the best fit. And what we find here is that there's some structured residual, which is common to some pulses, but not all. So I probably should have chosen a pulse where it fits perfectly for the animation, but alas, don't let the perfect get in the way of the good. This is the one that I did, and I've since lost that code. So we find a fit, right? We get our 4 parameters, and we can do this for several different pulses. We find, well, this one fits pretty good. Here we get some more of this sine Gaussian structure as well, but we've come up with a model where we can fit that as well, which is a sine Gaussian, as I've mentioned. Okay, so before I go on and apply this analysis to the candidate, which I already showed you, first I'll show you that actually it works well and it can reject candidates that you would otherwise expect to be gravitationally lensed. So both of these are two separate light curves, real data from the BATSE experiment, and you can see that there's this two-pulse structure, which you would expect. Well, hey, that looks a lot like some gravitational lens, especially this one here. But what we find is that we fit the fast rise exponential decay model. We see, hey, this two-pulse model here is actually a pretty good fit, but the one-pulse lens model, we're getting a lot more residuals, especially on the second pulse. So what's quite flat over here is quite bumpy over here. And we find that this is even in log base factor, that the two-pulse model is much, much preferred. Okay, and so if we look at the posteriors for the magnification and the time delay parameters, I said before we expect for a gravitational lensing that they will be the same. So we expect these four rings to be coincident for each of the different energy channels. But what we find in this particular case for this gamma ray burst is that there's a strong correlation between what would be the magnification ratio and the time delay. So that tells us immediately this is not a gravitational lensing event. Okay, so we expect from the equivalence principle they should be overlapping. So now we apply the same procedure to our favorite GRB 950830. And what we find is actually the one pulse lens model happens to be preferred in each of the different channels, although only slightly in the bluer channel. And we see again that all these posteriors are overlapping. So the black here is not the sum of the light curve, but actually it's each of the four of these different posteriors weighted and then multiplied together to get a final answer, right? So we've got a set of posteriors or a set of samples for the magnification ratio, a set of samples for the time delay, an equation which relates the time delay and the magnification ratio to the lens mass, right? So we run them through and we find that this black guy here, this black peak here, which is all the data taken together, gives us a 1 plus Z multiplied by the mass of 55,000 solar masses. So that is the lens mass is less than 55,000 solar masses. So if we take a reasonable lens redshift of a half or 1, what we find is this number becomes sort of 30,000 solar masses, which is very intermediate. So what did the lensing? There's three possible things which could be the lens, right? There's not very many objects in the universe which are reasonably compact and 50,000 solar masses. So one is a globular cluster, but actually there's not that many of them in the universe, right? So Milky Way has 200. You can work back and find, well, roughly the density of globular clusters is 5 × 10⁻⁶. So very small. Dark matter halos, we know there's heaps, right? We know that on galaxy scales, on galaxy cluster scales, the dark matter halos are doing most of the legwork in gravitational lensing, right? They're carrying most of the mass. But does that translate to lensing on much smaller scales by subhalos? And then there's intermediate mass black holes, which we don't really have an idea of how many there are in the universe, but we do strongly suspect that they exist. Okay, so well, first we can look at the optical depth. Okay, so the average optical depth, sorry for this equation, is the source counts integrated over all redshifts, source counts multiplied by the optical depth at that particular source redshift, integrated over all source redshifts. That's the number of lensed events. the number of total events, so the total number of sources, in this case, gamma ray bursts that you would count, is the number of sources integrated over redshift. Okay. And so the thing we're interested in here is the optical depth. And since we only have one candidate, we did a little sneaky and said, hey, this, and we also have no information on the redshift of our gamma ray burst. So we said this optical depth is going to be equal to the total number of lensed events divided by the total number of events. Okay. And what is in this optical depth equation is we're integrating over all volume. So the optical depth depends on what size we're considering. It depends on the number density. Well, where's my mouse? Number density of lenses in that space. So if we have a lot of little lenses or a lot of any lenses around, we get a higher optical depth. And that's also multiplied by the effective area of each lens. So higher number of lenses, larger cross section, then we have a larger optical depth. And that cross section is maximized when that lens is exactly halfway between the observer and the source. So if your lens is quite close to the observer or quite close to the source, actually it has a very small cross section because there's a very small window of parameter space where it will be able to create multiple images. So if we look at that in plot form, which is, I think for most people, much more pleasant and much easier on the eye, what we find, so each of these is the optical depth for a different redshift. So redshift 5 for the source, redshift 2, and so on and so forth. So our optical depth is roughly 1 over 2500. So we searched 2500 bursts, we found one, gives us 4 by 10 to the negative 4. So we scoot along here and we say, well, actually, since we don't know any of the redshift of the BATSE burst, because back then, it was the 1990s, so that wasn't really, that's not an option. But now, if we look at the Swift data set, the median of those is about redshift 2. So what if we say, well, hey, BATSE's median burst would probably about redshift 2 as well. So we go along here, we hit the red curve. Oops. We go down, we find, well, actually, we've got a lens density of 1.4 times 10 to the negative 3. And since our globular cluster density is way down here, we can pretty strongly rule that out as a lens. What that means is we'd have to see a lot more lensing events of GRBs with a similar mass before we expect that just one of those would be due to a globular cluster. Okay, so what about dark matter halos, right? I already said that, they're everywhere. They make up 30% or 25% of the mass density of the universe. Maybe it could be one of those. But most of that mass is locked up in the bigger halos, and of the smaller halos, actually, they're quite diffuse. So if we actually have warm dark matter, then the halo size is limited such that it couldn't possibly be lensed by something like this. But in the case where it is cold dark matter, which we kind of leaning towards at this point, what we find is, well, yes, there are plenty of these dark matter halos, but they're quite diffuse in the core, whereas the larger halos have the more compact core and a better gravitational lenses. So the halos exist, but they're poor gravitational lenses. So we toss that out as well, which leaves us only with an intermediate mass black hole. So from the plot I showed you before, we determined that we've got a density of 1.4 times 10 to the negative 3, which gives us a number density of about 6,000 per megaparsec cubed. Thus, there is approximately 100,000 in the neighborhood of the Milky Way, which is a lot, right? Okay, and so this is the publication that we got out of this. So it's very nice to collaborate with Eric on this. Check it out if you haven't already. That's all I have to say for that. So now, just within the last couple of weeks, there's been 3 papers on the archive, all looking at lens gamma ray bursts, each claiming to find one. So this is, and so in addition to being recent, they also have beautiful data, modern data. So our burst is 1995, this burst is 2020. So we've got Fermi, which is not shown here, Swift, which is shown here. This is another telescope, HXMT, and then I think this is Swift, oh no, sorry, Fermi spectra. So we have all this beautiful data to analyze. What we find, and so two groups found this particular burst, and so we find same GRB, same data, same super contribution, different authors, but the same conclusion is that it's gravitationally lensed. So they find slightly different masses, 470,000 from Wang et al. And 240,000 from Yang et al. Okay, so sort of on the edge of what you would expect to be intermediate. Okay, and so this is the data from Yang et al. This is from Swift, and this is from Fermi. And what is so very nice about this team of authors is that they've in fact used the software which I wrote for our analysis to create these plots. So you know, publishing a paper is one thing, but having someone use your software, I think, is another thing altogether. So here's a plug for that if you haven't seen it. It's built on top of Bilby, but it uses obviously is aimed towards gamma ray bursts rather than gravitational waves. Okay, so they also had spectra. So you can see here spectra from the first pulse, spectra from the second pulse. So that's something that we didn't have in our analysis, and just because the data weren't available, but it strengthens their result. Okay, so what they found is there's no spectroscopic data for this burst, but it was at redshift, sorry, they associated an object with it at redshift 0.384, right? And that's this thing right here. But what is probably more likely is that if it's going to be a lens, well, redshift 0.84 is quite low. Sorry, 0.384 is quite low. So if we look at this curve here, the orange curve, what that would mean is we have an extremely high density of these intermediate mass black holes. So what has probably occurred is that the GRB went off behind that galaxy and then was lensed by an object in the vicinity of that galaxy. And so if we can update our results here. So the black line is just with our one result, 1/2600. And so we find here they actually analyzed quite a large amount of gamma ray bursts, because they look not only in the Swift data set, which has been going since the early 2000s, but also the Fermi data set. So they've got a sort of 20 years of data almost. And so they found the one candidate. So the optical depth drops a little bit, and we infer a slightly smaller number, 5,000 intermediate mass black holes per megaparsec cubed. Okay, and here's a third one by a team out of Iran and Oman. So similar thing, right? One pulse and then copy pasted sometimes later, and they find that they've got 3.6 million solar masses. So a bit bigger here, and that's because the time delay is much larger. So our result was 0.4 seconds. The result I just showed you was a couple of seconds, and then this is 50 seconds. And that the time delay scales directly with the lens mass. Okay, so now moving forward from GRBs, this is some work by Geraint Lewis, and he was looking at, this is for fast radio bursts, but actually doesn't matter, it's just transients, right? So he's looking at high optical depth in a galaxy. And so you have a lot of stars, and they form this complex network of caustics. And he's asking, what is the distribution of time delays I would get if I have an object which is microlensed by this network. And so, as I just said, the time delay you expect is scaling directly with the mass. So in these normalized units, you have about 20 microseconds per solar mass. So giving you 20 seconds for a million solar mass objects. Now, interestingly, some work by Harish Vedantam and his collaborators showed that in these radio sources, they found this symmetric U shape occurring twice. And that's a very pathological shape that you wouldn't really expect in run-of-the-mill variability. And so they concluded that actually this is due to a microlensing effect. And so they looked at what light curves you would expect if you had binary black holes or binary point masses, and you had the object passing behind that. And so they were able to recreate a similar, so double U-shaped light curve. And so they infer actually a very similar number of compact objects to what we did based on this research. So it's good to know that, I guess, we're not the only ones that are finding this result. Not only are there more GRBs coming now, but this is being observationally seen in other aspects of gravitational lensing. Okay, so I've talked a fair bit now about what I've been doing and related research. I just want to talk about now, what could these black holes be? Where are the IMBH hiding? What are they doing? Why haven't we seen them? And so on and so forth. Okay, so we found this number density, 6,000 per megaparsec cubed. We know that the Milky Way formed from an overdensity of roughly 20 megaparsec cubed. So that gives us something like 100,000 of these black holes somewhere in the Milky Way, right? So here's a beautiful diagram of the local group I found on Wikipedia. And so we actually have a radius of 1.5 megaparsec. So here's us here in the beautiful Milky Way, and then Andromeda is up here. And so we do the volume of this sphere, 4/3 pi cubed, to get 15 megaparsec cubed. And the total mass is 2 trillion solar masses. Okay, and so our results saying, well, we've got something like 100,000 black holes of roughly 10,000 to 100,000 solar masses, which gives us a significant fraction, 10 to the 9 to 10 to the 10 solar masses in IMBH somewhere in this region. Okay, so we can do two things. We can say, hey, I'm going to throw them all into the galaxy. So Andromeda's got them all, Milky Way's got them all, but there's none in the intergalactic space. But obviously that leads to the problem of, well, why haven't we seen them in the Milky Way so far? Okay, so as I said, we can either put this 100,000 IMBH in the big galaxies, or we can sprinkle them around in the whole volume, hiding out in intergalactic space, sort of like the Reapers from Mass Effect, and only coming down to Earth or to the Milky Way every now and then, and perhaps quickly and rapidly ending up in the galactic core. So if we evenly spread these intermediate mass black holes over the volume of this sphere, we find that there's roughly just 3 in the Milky Way, which isn't, it's probably not so hard to hide 3, but you do have to consider where else in the IGM or in the local group that they would be. Okay, and you have to answer the question, well, how does the intergalactic medium and the outer halo become populated with intermediate mass black holes? All right, so some observational consequences. Well, if the mass spectrum of black holes and the intermediate range goes as mass to the power of -1, and you integrate that from 100 to 100,000, well, you quickly find that that's the whole mass of the Milky Way. So that's one issue. The relaxation time of a 10,000 solar mass black hole, 100,000 solar mass black hole is about 100 million years. So as soon as it gets into the galaxy, it's very quickly spiraling and ending up in the core. And if these things are then in the core and merging with Sagittarius A star, well, just 100 of them will double the mass of our supermassive black hole. So very quickly, you're potentially running into problems which observationally we haven't seen. Okay, the gravitational influence, which would lead to tidal disruption events or disrupting star clusters, isn't so big, just 0.01 parsec. And for microlensing, so we expect every now and then of all the stars we're looking at in the Large Magellanic Cloud, sometimes objects pass between us and the star, causes changes in the light curve, which we expect to see. So far, nothing of this mass range has been seen, but I'll talk a little bit more about that later. So if the Milky Way is an average galaxy, then probably intermediate mass black holes don't live in the bulge or the disk of the galaxy. Okay, so wandering black holes. What are they? Where do they come from? On the left here, I've got a picture taken by Hubble of a galaxy merger. And what happens is, as the two galaxies are merging, each of them has their own supermassive black hole, or in the early stages of the universe, perhaps intermediate mass black hole, or several living in the nucleus. And then as they merge, as the galaxies merge, either the black holes will merge, or perhaps one will get shot out. Okay, and or if the two black holes do merge, the merger product can be released with a kick velocity of up to 5,000 kilometers a second for equal mass black holes. So I'm going to quickly run you through some simulations, but keep in mind that resolution is limited to 10 to the 5, 10 to the 6 solar masses. So they don't keep track of black holes smaller than that, although the results are still extremely interesting. Okay, so these are large black holes that are physically offset from the center of the halo, and mergers is one very good way to get them out there. So this is some work by Michael Trammell and collaborators, and what they find through their Romulus simulations is actually of a Milky Way type galaxy, we find 12 supermassive black holes of roughly 1 million solar masses within the virial radius. And that's not counting those that are in the satellite halos. So potentially in our own Milky Way, there are 12 supermassive black holes somewhere where we haven't seen them, just lurking. And so these black holes can exist even within the host galaxy they find for several billion years, that are often accreted by the host halo early in the universe. But they're typically at large distances from the core. Okay, and what we find is that there's a correlation between the number of these objects and the mass of the halo. So small halo, 10 to the 11 solar masses, not many black holes, just the one in the center and then two extra. Something our size, we have closer to 15, and then a 10 to the 13 solar mass, you have close to 250 wandering supermassive black holes, million solar mass black holes, floating around the galaxy. Okay, so these are seeded by local gas properties and allowed to evolve. And so what we find, one key result is that the host galaxy is stealing the stellar counterparts, so any stars that will be around that black hole at the virial radius. Okay, so how can we detect these things? So first is through the accretion of gas. So if we have a black hole wandering in the outer halo of the IGM, it's traveling through very diffuse, low density gas, but it still will have a observational signature. It's still eating, still feeding, still going to be emitting light. Or it could be observed through the cluster of stars, which are tightly bound to that object. So say you have, say it's formed in a globular cluster, the cluster dissolves into the galaxy, leaving you an intermediate mass black hole, and that's going to be surrounded by some of the stars that were very tightly bound to that. And due to mass segregation, that's probably more likely to be small black holes and neutron stars, so the denser, heavier things. So it might be a bit difficult to detect, but we still expect to see something like that. Or could it be gravitational lensing, either through gamma ray gamma ray bursts or transients, as I've already spoken about, through gravitational lensing, looking at microlensing in the Magellanic Clouds like Ogle, or through VLBI jets, which I'll talk a bit more about in a second. Whoops. Or through disrupting star clusters, so punching through, taking some stars, dissolving the cluster, or through tidal disruption events, such as this beautiful image I've taken from some work by David and Daniel and Ilya, right, leaving this beautiful tidal disruption event. Okay, so first looking at the accretion method. So these are some simulations of a 10 to the 5 solar mass black hole in the galactic outskirts, going through low density gas, reasonable temperature. And what they find is that due to the distribution of the angular momentum of the gas that's accreting onto that black hole, it quickly becomes turbulent and is inefficient. So it's visible, but not as bright as what would be maximum. It's not close to that. So on the positive side, ALMA is very sensitive and has the spatial resolution to detect this, but the detectable mass limit is 100,000 solar masses, but we still have to find these objects in, over the whole sky, which is the difficulty. Some work now by Jenny Green, looking at the trying to find intermediate mass black holes through the clusters of stars, which are expected to be bound to these wandering black holes. So they're searching for sort of a few thousand stars that are expected to be bound to these black holes, and they predict roughly 100 within the Milky Way, although they find no candidates. But the limiting assumption is that the star clusters remain bound to that black hole, they don't dissolve, assuming that it is stars rather than stellar remnants, so that they would all be visible rather than dark remnants, and assuming that the cluster is 1 parsec in radius, which I think is a bit large. But anyway, very interesting. And okay, and gravitational lensing. So spoken about this a bit. There's some work from Ilya and Bukash looking at dark objects which have been microlensed, or which have their presence has been discovered through microlensing. So they find objects that are a few solar masses, but they're dark and therefore likely black holes or neutron stars. Okay, so the optical depth to the Magellanic Cloud is about 10 to the -6, large Magellanic Cloud, but the event duration scales as mass to the power of a half. So shorter events due to a smaller mass, larger mass, longer events. And the event rate per star that you're observing, seeing if there's a microlensing event like this in its light curve, will be the optical depth divided by the event duration. So for larger mass objects, the event duration is larger, so the event rate per star becomes very, very low. So either you have to observe a lot of stars in order to see this just once for a 10 to the 4, 10 to the 6 solar mass object, or you have to be very, very lucky. So now onto VLBI jets. These are 2 images from a gravitational lens quasar. So these jets are both the same image. And this study by Joachim Wamsgans and Paczynski showed that, well, if a significant fraction of dark matter is locked up in million solar mass black holes, we expect to see the jets to be distorted differently in detectable ways by those million solar mass objects. And then, so another study then followed that up. So this is 1991, 1994. And what they found is that there must be less than 10% of bound in these objects in the halo of the lensing galaxy. Okay, and just quickly on tidal disruption events, the time is scaling as mass to the power of the half. So it's only roughly 4 days for a 10,000 solar mass object. So there's not a very big time window to observe it. But one very interesting thing is that a white dwarf can only be tidally disrupted by a black hole smaller than 100,000 solar masses. So if this is observed, it's very good evidence for an intermediate mass black hole. Okay, and Lisa, so obviously gravitational wave events of black hole mergers have done a lot for astrophysics. Lisa in the future will show us not only intermediate mass black hole mergers, but also supermassive black hole mergers. So this is just a plot of the sensitivity for various masses. We find that this will be useful in determining either IMBH mergers in the early universe or IMBH supermassive black hole mergers as they get accreted by the galaxy and make their way to the nucleus. Okay, and so Lisa's sensitivity will be with merger products of 10 to the 5, 10 to the 4 solar masses, which is exactly the range of black hole which we detected in our study. Okay, and so Lisa will also have the opportunity to see these events for months before they occur, allowing us to detect them both in electromagnetic radiation and gravitational waves. All right, so we have LIGO looking at black holes on the smaller end of the intermediate mass black hole range. On the larger side, we have dwarf galaxy AGN. So these are the black holes in the nuclei of very small galaxies, and LISA as well. And then we have sort of accretion, gravitational lensing, and tidal disruption events, which could be showing us more information about sort of 1,000 to 10,000 solar mass objects. Okay, so just to finish up, I'll talk about the possible formation mechanisms of these massive black holes. And so there's three leading scenarios at the moment. So on the right here is a very famous diagram by Martin Rees of all the possible ways you could end up with a massive black hole. Okay, but the three main ways I'll be talking about right now are gravitational runaway, remnants of population 3 stars merging and ending up with supermassive black holes, or the direct collapse of gas clouds. And these will have different signatures in the number density scaling with mass, black hole fraction scaling with the galaxy mass, and the black hole, central black hole mass, I think the last one is. And so this is a review by Jenny Green. All right, so gravitational runaway, I sort of spoke about this before. Say we have a globular cluster or some other cluster of stars. As the larger stars will evolve, turn into neutron stars, black holes, they will become segregated and sink to the core of the cluster, and the lighter stars will evaporate or raise to the outer layers of that cluster. And then in the core, you have many body interactions, the black holes potentially merge, and then you end up with the 10 to the 3, 10 to the 4 solar mass object. Okay, and we see that this particular number density is midway between the other two. So by probing the lower scales of sort of 10 to the 3, 10 to the 4 solar masses and filling out that function, we can determine which of these three scenarios is most likely or the main component of forming intermediate mass black holes and then supermassive black holes. So population 3 stars, the first generation of stars, very pure hydrogen. They can leave up to around 100 solar mass black holes. And then such an object would need to consistently accrete at maximal rate, at the Eddington rate for its lifetime, with periods of super Eddington accretion in order to reach, a billion solar masses or more. And finally, the direct collapse. So if you have a very big cloud, we know usually that of gas, usually it will collapse, heat up, fragment, and make nice little stars such as the sun, which powers all life on Earth today. But if we have a very pure cloud, metal-free, and it's collapsing, we also need some UV flux to destroy molecular hydrogen that would form. It can collapse and possibly directly form a 10 to the 4, 10 to the 6 solar mass black hole. And that has a characteristic number density function as well. So to summarize, we found evidence for a gravitational lens gamma ray burst, and we conclude that it was lensed by a roughly 50,000 solar mass intermediate mass black hole. We infer the intermediate mass density, mass black hole density of roughly 6,000 per megaparsec cubed. Other authors are finding more lensed gamma ray bursts, and indeed other signatures of lensing by objects of 10 to the 4, 10 to the 6 solar masses. Lensing is one of the few ways to directly constrain the number density of intermediate mass black holes, which gives us information about which of those 3 scenarios I just spoke about is leading to the formation of supermassive black holes. So the future is exciting, and especially through detections of wandering black holes and massive black hole mergers, there's a lot to be discovered. So thank you for listening.
Thank you very much. Yeah, it was a fantastic talk. Yeah, Daniel also said it's a fascinating talk.
Thank you.
I'd like to open for questions. Nikhil has a hand up. So.
Hi, James. Really nice talk. I just have a question about your fitting procedure and some of the other papers, what they're doing.
Yep.
Do you take into account the response matrices of the detector and
Oh, sorry.
Sorry, can you hear me?
Yeah. Sorry, I interrupted you. I didn't realize that was not the end of the question.
You can answer just that part first.
Okay.
Maybe that. Yeah.
So I personally didn't, because we were looking just at the light curve. I did sort of dig into a bit of spectral modeling where it is a lot more critical to do that. But we ended up not looking at the spectra of our particular trigger because it was quite, I think that the data was pretty low quality, so we didn't follow that up. So I didn't look at that spectral folding sort of stuff, but I think the other teams would have.
And do you know if there is any reason for? So I'm not worried about the BATSE one in particular. I'm worried about the other one. Do you know if there's any reason why the one that was observed with Swift 2021, why that particular GRB, the second exponential, can't be just the extended prompt emission that you also see for the gamma ray bursts?
You mean just the second pulse?
Yeah.
So I think they did actually use the software of like the pulse fitting thing that we made. So this one.
Yeah.
So I mean, you can see these curves here. I don't think they really spoke about it in their paper, but just by the fact that, you know, I wrote this software and I know how it works, I'm imagining that they did get an indication of the, because they've done the fits, right? So, you know, it's automatically giving that information to them. So I didn't see it in the paper, but I'm pretty sure they would have.
But so the reason I ask is because if you don't take into account the spectra, the response of the detector appropriately, then one pulse, it's quite easy to get one pulse that in intrinsic space doesn't look anything like another pulse to start mimicking it when you reduce it down to the counts versus second space.
Yeah.
So yeah, that's the reason I asked. I don't think it'll be a problem for BATSE, but I imagine it could be a problem for Chandra and Fermi and Swift. That's interesting. I'll have a look. Thanks.
Yeah, so Daniel also had a question on chat. Do you want to read it out or should I?
Yeah, can do. I was just curious. I mean, you seem to be suggesting that there should be several sort of similar mass size black holes to the one already in the center of the Milky Way wandering around. Yeah. Is that the right understanding, or are you saying it's more like a population of, 10 to the 4, 10 to the 5, which could be probably easily hidden?
Yeah.
I mean, what is
well,
the population of black holes that you expect from a cosmological simulation? Do you expect more intermediate things or more?
So the simulations which I spoke about, they were limited at 10 to the 5, 10 to the 6 solar masses. So they were saying, I think, that these things are million solar mass black holes. I'd have to double check, but I'm pretty sure.
So they're of comparable mass to the Milky Way's black hole.
Yeah, exactly.
So it wouldn't. How can we miss them? It seems bizarre that we could miss, other ones. But,
yeah. So one thing I forgot to mention actually with our number density, and it ties into the optical depth, that the lensing is maximized when something's halfway. So it could very well be that the number density of lenses is quite high at redshift 1, and since then they've all made their way to the center and been absorbed into the central black holes of all the galaxies. But in terms of this particular work, I'm not sure. I'm pretty sure it was million solar mass objects, and they were preferentially sort of. I mean, here you can see where they are with relation to the disk, but I don't have more information.
yeah, fascinating.
But I thought it was really interesting when I stumbled upon this paper. And presumably the since they're resolution limited, there's also a greater number of lower mass black holes, which will become apparent in the future. Ilya has a hand up.
Yeah, I thanks very much for the nice talk, James. So I was trying to do a little estimate as of sort of how often, if you imagine order of 1,000 kilometer per second velocities for these wandering black holes, how often they would come into the Milky Way proper, let's say within 10 kiloparsecs kind of thing, and given the number densities you're suggesting, and the answer seems to be order of magnitude once every 100 million years. So what I haven't done, and I would like to do, is to figure out whether if something like this, for example, crosses through the Milky Way, will it necessarily get stuck in the Milky Way? Because of course there are things like dynamical friction and so on that would mean that the velocity decreases, and even a previously unbound object might become bound as a result. But I am still curious if how we are managing to observationally hide all of these sources. I take your point that they're not going to be very bright accretors if they're sitting out in the intergalactic medium, that the number density is so low there, less than 1 ion per cubic centimeter, that the accretion rate for something moving along at 1,000 kilometers per second, the Bondi-Coyle accretion rate is less than 10 to the minus 10 solar masses per year. So fine, it's basically invisible. But once they get into the Milky Way, it just seems strange that we're still missing them, even if they're sitting out in the halo predominantly, not in the disk. So, and in fact, they're not, as you said earlier, not mass segregating down, or through dynamical friction moving down and eventually merging with the massive black hole, which would also create a problem, because there are enough massive things merging with the massive black hole. As you said, the massive black hole mass, tells us, well, it can't have merged with too many heavy things, right? If it's merging with even 1/10 to the 5 solar mass object in 100 million years, would already it would already have a mass that's higher than its currently observed mass, right? So anyway, I think it's really interesting stuff, and I think it's still very interesting how this all hangs together. Thank you.
Yeah, thanks. Yeah, I think just off the cuff, I think what I said before about all these lenses are at much higher redshift, maybe that could be worth further thought. But yeah, I'd have to do some soul searching, long hard thinking to get an answer.
Okay, we've actually past the hour, but I have one short question.
Yeah.
So the long delay time one that was found is like has like a 20-second or something delay, right? Are there any like searches for like 1,000-second delay ones, like
Yeah.
for like this proper supermassive black holes?
So yeah, when basically when I submitted the software PyGRB, one of the reviewers, Michael Burgess, just I don't think he knew what I was planning to do with it. It was just light curve fitting at that point. He said, "Yeah, I don't think there'll ever be a gravitationally lensed gamma ray burst." And the reason for that is because as soon as you have two detections, so once your time delay is too long, you have two separate events, and there's a whole host of different calibration things. You know, different point in the atmosphere. You know, if your orbit's 90 minutes, you miss a large window. Although that's obviously, since there's a few satellites up there now, not such of a problem. But even comparing data taken on Swift versus Fermi, for example, it's quite difficult, and the spectral folding that takes place that Nikhil mentioned means that, and Michael Burgess wrote a paper about basically what are all the different things we're taking into account when we're calibrating a GRB spectra, and it makes it quite difficult when you have two separate events to really identify them as the same thing. But I mean, I'm sure in the future it will be possible. I mean, especially if you're observing them at multiple satellites, you can build this sort of abstract idea of what the photon flux is.
Yeah, thank you.
Thanks.
All right, if there's no other urgent questions, then let's thank James again. Yeah, thank you for the very, very exciting talk. And yeah.
Thanks for having me. I'll see you later.
And see you all.
Thanks, Rio. Bye.
Bye.